calculus. We are going to do intermediate value theorem today. I almost said international value theorem. All right, for the intermediate value theorem, we've got a couple of different theorems that we learn in calculus. The first of which that we're going to explore is the intermediate value theorem. I'm going to write out the words first. It's going to sound big and scary, but I think once you see the visual of it, you're going to see that this makes 100% sense. So here are the words. If f of x is continuous, and we've been just talked about continuity, so you know what it means to be continuous. So if f of x is continuous on an interval AB, and f of A is less than L is less than f of B, or f of A is bigger than L is bigger than f of B, then there exists a value of C on the interval AB, this time not including A or B, such that f of C equals L. Told you it would look scary, did I lie? I did not. So if f of x is continuous on AB and f of A is less than L is less than f of B, or the vice versa, f of A is bigger than L, which is bigger than f of B, then there exists a value of C on AB such that f of C equals L. So I'm going to do this one first, where A is less than f of B. So let's just put in the first quadrant for fun's sake. Here's some graph that's increasing. I know it's increasing because f of A, my y value at A, is less than my y value at B. So here's my A. So that makes this guy here my f of A, my y value at A. Right? Let's call this point here B, which means this point over here is f of B. And so all this says is if it's continuous, which means I can draw it without picking up my pen on AB, so if it's continuous between here and here, and we can find some L that's in between f of A and f of B, such that the C value has to exist. So that value at when x is C has to be equal to L. So if I pick a point between the two x's, there's got to be a corresponding y value between the two y values, right? And that's only true if it's continuous, because if it's discontinuous, all bets are off. So we're going to investigate a couple of graphs. So this part here, it would be the same thing, except for instead of my graph going up, I'd have a graph that's going down. The same concept applies there. All right, so let's investigate the graphs below to determine if the theorem is applicable. So in order to use it, we got to make sure we've got all the conditions met. So first, for this piecewise function, it says, is there a value of C on the interval from -5 to 2 such that f of C is equal to 2? So is there some point where y is equal to 2? Yes, right there. So we can say yes. There is a value of C on the interval -5 to 2, sorry, not -2, +2, such that f of C is equal to 2. So we've got some value, right? Where f of C, we're going to call this guy C, is 2. This is my A value. My B value is here at B. All right? If that's true, does the IVT guarantee a value of C such that f of C equals 2 on the interval -5, 2? Yes, the IVT says that, but what has to be true? What was the very first part of this? If f of x is continuous on AB, if we look at our graph, is f of x continuous on this interval between A and B? No, we have a discontinuity, right? Where's our discontinuity? Right here. What kind of discontinuity do we have at -2? A jump discontinuity, Miss Horace. All right, so I'm going to say IVT does not guarantee the existence of C on -5, 2, such that f of C equals 2, because, why? Because f of x is discontinuous, or you could say is not continuous, either one, is discontinuous at x equals -2. Which, what? Is in the interval -5, 2. So, yes, the value existed, but even though it does exist, IVT did not say it had to exist because it does not meet the very first requirement for IVT, which is that it's continuous across the entire interval. All right, look at number 2B, whatever this is. Is there a value of C on the interval -1, 5? So here's my A, here's my B, such that f of C equals 2. So between here and here, do I have a y value up here at 2? No. Whoa. Love the smartboard. No. All y values on the interval when x is -1 to 5 are negative or less than 0. So none exist such that f of C equals 2. All right, so does the IVT guarantee a value of C such that f of C equals 2 on the interval -1 to 5? Why or why not? All right, so even though we are continuous this time, right, we've got the continuity part, no jumps, no breaks, no infinite discontinuities. So even though we're continuous, our y values are not in the right area. So although f of x is continuous on -1, 5, what is our f of -1 value? Because remember, we've got to be able to find an L value that's what? Between f of A and f of B. So f of 1, f of -1 is right here. It's approximately, let's call it -1/2. And f of 5 is equal to, what would you call that? -3.5-ish? So f of C equals 2 is not between those two numbers, right? Between f of -1 and f of 5. Thus, or you could say therefore, IVT does not guarantee the existence of C on interval -1, 5. All right, so think about these two. I want you to go ahead and pause your video. See if you can come up with, based off of what we just did, what two conditions must be true to verify the applicability of IVT. So sometimes part of it can be true and it exists, sometimes it doesn't. What has to exist in order for us to say, I'm going to use IVT to prove something?